Okay, well, I think, do we have Scott? Are you back?
Yep. Should we
Okay,
get started with the next
yeah,
session?
yep. One more question before we get started. I didn't see the full question.
Yeah, there's a question, how to know which stations are out there that recorded the event of interest.
So it's, I think, well, it's difficult to know um, which events a particular station has recorded. But the typical idea is you would uh, go to where the earthquake is, and then you could find of nearby stations. And some of the links that we provided, the ANSS station map and the Southern California station map, would give you some idea of which stations exist. Um, if it's a large earthquakes, I mean, are recorded around the world. So basically, magnitude 7 and larger. Um, it's should be recorded by most broadband stations. So it'll be low amplitude, but certainly potentially detected. But the other idea would be to go to a collection of earthquakes. That, as I mentioned, often when there's a large earthquake, research groups will make a collection and say, here's basically stations, records from stations that have good recordings of that earthquake. And that would be another way you could search for the earthquake that you're interested in, and that would you'd be able to find a collection of seismograms from stations that recorded that event. Okay, well, let's go on to kind of the next main topic here for today's session. So let's see. I'm going to share my screen. So this session, in some sense, continues on the theme that seismology research is data and computationally intensive activity. Um, so I'd like to present and give a kind of an introduction overview to kind of different aspects, the importance of research computing and seismology, and address the topic or address the topic through these um, summary areas. So I'll talk about the importance of research computing skills, uh, mention the recognition of there's an open science and open source value system it's worth knowing about. Talk about seismological software development best practices, and then some brief comments on basically looking forward, potential important future trends for research computing and seismology, just to have kind of a forward-looking aspect to this. So let's touch on kind of the importance of software and research computing skills in seismology research. So based on my experience, I've worked in the field for several decades. Um, to me, there's kind of an underlying skill set that's very valuable if you want to do seismological research. So as far as computing skills, the kind of the anticipated or the expected kind of baseline is you're able to work at a command line in a terminal window on a computer running a Linux operating system. So this is the way it's been done for 20 years. And I anticipate this is going to continue because typically this is how the interface or the computing, particularly operating system that is used on both cloud and supercomputers. So this ability to work on a command line in a terminal window is basically a very valuable and essential skill. Um, Also, the ability to compile and run software using GNU compilers. Before Science Gateways, typically you would download research software from, say, GitHub, but you need to build it. You need to compile it and get it running on your computer. And typical environment is open source compilers, GCC. So ability to work with that and have experience is valuable. Being able to run and potentially modify software, Java and Python are commonly used. So, but basically the ability to run, you know, s- software that's been developed by research community. So, which is different than running, let's say, shrink wrapped or commercial software. Um, and then the ability to write software in a language, one language or another. It's it just is a great advantage if you're able to write even a small program and get it running. It allows you, gives you a ability to do things not possible if you're not programming. So we're not teaching these skills here today, but I want to point to this excellent reference, learning resource, software carpentry. And if you go to that link, one of the kind of lessons, introductory lessons, is working at a Linux command line. And so this, even though software carpentry is domain independent, the material you found there is most likely useful for a researcher in seismology. So I want to make a distinction about the kind of the spectrum of software skills, um, you know, there's- which start with the ability to use software. So we use seismological researchers use a great deal of custom open source software. You'll be introduced to several of those here during this workshop, including Sysol, Tandem, Moose Farms, USurf, PyCSIP. All of these are um, open source codes, and again, it's different than using Adobe or Microsoft tools. Um, uh, because they're basically custom and developed by the research community. But using this existing software is one level, but then developing your own is a great advantage. So when I talk about open science and open source, I like to just point out and express that basically the open science and open source world involves a, a value system, and it's not so, and it's very, at least it's important to be aware that you're working in a community that has a particular value system. So one way to illustrate this is there are alternative views on open source software and the approach. This is highlighted years ago in a letter that Bill Gates wrote to what was called the Homebrew Computer Club. So he wrote this almost 50 years ago, in 1976. But the idea was the Homebrew Computer Club had a software approach that said, we're going to develop software, we're going to share it. Other people are going to be able to see our software and then they'll build on it. And that'll allow us to make rapid progress. But in his letter, Bill expressed, a different perspective, that programmers must be paid for their work. And if you want good software, you should be willing to pay for it. And if you haven't paid for my software, don't use it. So, I mean, both perspectives have their own value, and but if you're working in the seismological research community and the open source and open science, it's the value, the pervasive value system is definitely this homebrew software perspective. So, the reasons the community feels this is so important is it's in some sense consistent with scientific process. So part of the scientific process is allows peer examination and review of work. We are not expected to accept someone's result, uh, as if it came out of a black box, or uh, some unknown process was performed and now I've got an answer. The scientific process kind of insists on the ability to review what's actually done, and open source and open science supports that. But also there's the idea within the open sciences, programming resources and computing capabilities are a limited resource. There's just not enough funding and support for us to redo each other's work, and there's also kind of a importance that we make progress. We work in seismic hazard research, and we want to um, provide information and useful information before the next big earthquake happens. Um, and so to make rapid progress, we don't want to duplicate. We want to build on, as someone else makes progress, we want to build on that progress. So this is the value system that we find most commonly within the open, in the seismological research community. You don't necessarily have to share this, but you should at least be aware of that's the value system you're working in. Okay, so I'm going to touch on seismological software development best practices. Um, within SCEC, our aim is to use good open source software development practices and apply them consistently. If we do this, it helps to ensure that our software is maintainable by the research community, even if the original developers are no longer involved. So much of the material and the topics I'm going to talk about here are what is taught in a computer science program as software engineering. It's not, so if you take a software engineering class in the computer science field, they don't teach how to program. They teach you a lot of the other activities associated with developing good software and making it maintainable. I- Um, and this is an expression here in this box here about a wide variety of terms that are used: best practices, open source, sustainability, managed code, build. Um, best practices is maybe a difficult term because best is subjective. Um, but I'm going to describe what, in my view, has been agreed upon. There's general consensus within the seismological community of um, good practices, or what are sometimes called best practices. So just so there's a reference down here at the bottom to the Molecular Sciences Software Institute. They've got their own kind of material and descriptions of software development challenges, uh, which is just an indication that this is a multi-domain. Good software practices are a multi-domain challenge and issue. So within the seismological community, there's an organization called Computational Infrastructure for Geodynamics, CIG. It's an NSF-supported research organization, and they've defined a series of best practices for seismological software. And we rely on their kind of statement about where they've identified these standard practices. And I think it's convincing that if we use those practices, our software will be more easily used and more sustainable. So this is kind of an outline of the best practices that CIG has identified for our research community. On the left are basically the um, areas that are practice areas. Um, so a wide variety of things: licensing, version control, coding, etc. But what I want to show is that basically they defined a spectrum of practices. You start with kind of minimum, bring your code up to the minimum practices, but as your code matures and potentially attracts users, you will kind of introduce and adopt more standard practices, or the target practices. So this is a list. If we summarize the practice areas they've described, they're here, ones that they've mentioned. There are some additional standard practices that are emerging and are likely to be added here in the future. Um, so let me kind of give an overview of some of how SCEC makes use or applies some of these best practices. So um, I want to start with software licensing. So when you deliver and develop research software, if you want others to use it, it's important to include a software license. If there's no license, the software is assumed to be private, and commercial government agencies, many research communities will avoid using your software. It doesn't have a clear software license. Um, and we want to have broad impact, so we want to permit others. We want others to use it. So SCEC has adopted use of software licenses for our codes. Software licenses get into legalese, and many of us would prefer not to deal with legal issues like this, but at a minimum, it's worth recognizing kind of the spectrum of licenses. So if we start or over here on this spectrum, all the rights reserved, those are the private software. So this is software maybe from Microsoft or Adobe or IBM. Basically, um, often, uh, so commercial codes have all rights reserved. But then there's another spectrum goes over to the right, which is in public domain, and so basically that's distributed, and you're free to do with it what you want, including sell it if you feel you can sell public domain software. That's permitted. Um, some comments in here about what's the difference between free and open source, which I'm not going to go through the distinction clear here. We prefer the use of open source software. Um, when we get awards, software development awards in the past from National Science Foundation, they have one of the requirements, if they fund us to develop software, one of the requirements they give us is that we need to put an open source license on our software. But the NSF does not want to define themselves what an open source license means or what the actual terms are. So basically, they rely on this organization, Open Source Initiative, OSI, with the link here at the bottom of the page. So that's a organization that identifies and defines software licenses, and they have a collection of licenses that they view or consider open source, and NSF agrees if you use an OSI open source license, you're compliant with making your software open source. So this is kind of a collection of different types of open source licenses. All of these are OSI approved. As I mentioned, SCEC's default, or I will mention now, the SCEC's default is the second one, called we use the BSD 3 clause license. It's for a legal document. It's really quite short, 3 clauses or 3 paragraphs. It's considered a permissive license, which means that people are free to copy your software and to modify it and potentially to redistribute it, as long as they acknowledge that it started you. It's based on code that they got from you. Okay, so the next area and best practices relates to version control. So version control for software, it's a basic practice used by experienced and professional software developers. Um, and so version control helps you keep track of changes and store previous versions of your code in case you need to work backwards. Um, in the previous days, we would send tar files around or zip files to distribute our software, but now committing your software into a version control system is considered a basic practice. Within the seismological community, the open source standard is version control system is called Git. There's a public service site called GitHub that provides a Git version control system. It's widely used within the research community. It's worth noting there's a distinction between GitHub is basically the version control system, and so Git is the version control system, and GitHub is a service that provides the Git version control. You can use Git without using GitHub. For example, there's a GitLab service, I believe. You can implement your own Git server, but for practical purposes, working with GitHub is a very valuable practice, or is a commonly used practice. But once you've selected Git as your version control, there are other steps. You also need to define your development approach and your branching model. Um, I'll briefly describe some of those issues, but this is not a kind of tutorial on how to do that. So let me start here. It's kind of evidence of SCEC's open source and our use of version control. Uh, Checked recently, SCEC has 64 public source code repos on GitHub. This is kind of the homepage. It's called SCEC Code. And basically, these are research codes that SCEC research community has developed, and we're providing them open source here on GitHub. As usable in their current form, but also potentially something that you could start with and extend for your own purposes. When you use Git, it even those of us who are been doing software development for a long time can be intimidating learning it. There are certain concepts and behaviors that you need to learn. In my view, Git it takes common terms such as clone, pull, and push, and you have to learn what it means when you issue that kind of command. I think there are some kind of essential concepts and practices that help as you work with Git. One of the key ideas with Git is that it stores files in multiple locations during development. And when you're issuing various Git commands, you're moving files between these different storage locations. When you work with Git, one of the key decisions you need to make is how changes are added to the code base. And so there's different approaches. You can clone the repo and then push it back into the repo, or you can fork a repo and then give someone a pull request. So that takes a little bit of learning to appreciate which code practice you want to use for a project. But it will come up quickly when you work with others on a software development project. There's a software branching model, which is how you kind of develop different versions of the code. And there's important process of merging. When you've got two versions of the code, you need to combine them and create one version. There's a process for merging conflicts, and that which needs to be done routinely. So these are some kind of issues that you, even once you've decided to work with Git, there's still some additional decisions and practices that you need to develop and get familiar with. To me, I just point at this, won't go through the details, but I want to express this idea of that when you work with Git, it has files in different locations. So as an example here in this diagram, there's a yellow repository that it's labeled here the remote repository, and this is the repository on GitHub. So that would be SCEC's GitHub UCVM. But if you want to work with that code and modify it, basically you make a copy onto your local computer, and then so you've got a version of the code in the green file, which is labeled local repository. And then when you're making edits to the local, you move it into your workspace. And so Git has these commands for moving files between these different locations, and kind of figuring out how that actually, what those commands do is an important part of working with Git.
You have 5 minutes
Another,
left, Phil.
oh, I'm sorry. Okay, so I'm going to skip through because I want to just save a little bit of time here for to talk about future trends. So another issue is relating to how you do different branches of the software. If you're developing, you got maybe a released version of the code, but then you want to add a new feature. You don't want people running into incomplete code. So the way you handle it is to develop different branches. And so as you get into working with code bases, having a branching model is important. I want to touch on GitHub Actions. So it's becoming a standard practice. When you commit code, you also develop some tests that confirm that the code is working properly. And what GitHub Actions provide is when an event happens, it'll automatically run tests that you've defined. And the event can be a new version or of a subroutine or a code was checked into the repo. And so that is the event that triggers the test they're running. And GitHub Actions supports the ability to run a sequence of tests. And so they consider those workflows, and you can define a series of workflows that occur um, after a new version of code has been checked. And that helps ensure that changes haven't broken your code. You can, this is evidence for this is shown often on Git repo. So here's an example from CSEP where there's a badge here showing that their tests are running. And here's another example from one of our UCVM codes showing that the UCVM CI tests are running and passing. So that's a good thing to put on your code. That helps convince people your code's working properly. Um, Another issue and often considered is how much of your code has tests, and there are tools for helping identify um, how complete your code test coverage is. Um, Touch briefly on documentation. Um, this is an example of CIG of it, where they develop kind of standard. They have defined a standard format for software documentation. This is a great advantage for a code. If you've got good documentation, it indicates much more mature code base and likely to attract users. Standardized software manuals require significant time and effort. They indicate maturity of your software. As an example, within SCEC, we use we've got just defined the standard contents for our GitHub repo. When we create a new repo, we ask for put a README, links to the software documentation, a code of conduct, some continuous integration tests, information on how to contribute changes, clear information on how to install and run the software, and information on software support. So this is common information you should find in any of our Git repos.
I want to let you know you're at time, Phil.
Okay, I'm gonna run a little bit over here, but yeah, thanks. I think we'll still have time. I don't think we'll have any problem getting through the exercises. As far as documentation, just kind of the key recommendation is who's your audience? Ask before you start writing documentation, figure out who are you speaking to, and what is the goal. And this is kind of a outline and a diagram of potential breakdown or different targets or information content that your software documentation might be aimed for or might be trying to provide. Um, Important. I'm going to want to point out the importance of that both software and data sets are now typically assigned digital object identifiers. They're considered persistent. Storage location for the software or the data may change, but the software and data remain the same and the DOI remains the same. DOIs are issued by authoritative organizations that are willing to manage software and data over a long period of time. At this point, SCEC does not issue DOIs, but we go to external organizations that issue DOIs for us, for our products. Here's an example of Zenodo, one of our software that's been registered in Zenodo. And if you go there, you look at PyCSEP, find the software product, you'll have a DOI citation, a rights statement. Similarly, important data sets now are expected or should have DOIs. This allows people to reference your data set in their publication. And here's an example where we've done that with a data set. This is on the Design Safe. We have a collection of ground motion simulations, and we've got a DOI. So anyone that uses this can reference our work and in some sense credit us. Kind of related topic is mentioned this previously, but basically hosting or posting your information in a research data repository helps make it more findable. So for example, the USGS has developed what they call the Science Data Catalog. You can go there and you can search, and this, you can find research data sets that have been developed by USGS researchers. So, but this use of a centralized repository is, significant advantage. It's much easier to find data set if it's in a repo like this than it is if it's posted on maybe your academic website. The USGS has their repo, but they're want to make you aware that there's a variety of other earth science data repositories and that might be appropriate for your research data. I think this is the last topic on the best practices, the idea of reproducibility, computational reproducibility. I want to start with the terms reproduce and replicability can be used in different ways. This National Academy of Science is a kind of a reasonable referable definition distinguishing between reproducibility and replicability. Basically, the idea, again, is there's a spectrum of reproducibility for research. If you put your research just in the publication and if it's computational research and there's no software, it's considered probably not reproducible. But if you have a publication plus code, it becomes more reproducible. And as you add code and data, you kind of advance up the spectrum. These are some comments about the tools to create or to allow people to do reproducible calculations are being developed. They often are heavyweight, but this is one of the capability of science gateways. They can help produce and support reproducibility of research with workflows and data. And that's one of the reasons that gateways may be of great value going forward. Okay, well, I know we're long. I'm going to go, let's say, another 5 minutes here before we get into the exercises, just so we have a moment to talk about some potential future trends for research computing and seismology. So I want to mention this. There's an organization called the Open Science Framework that's designed to support open science practices. In my view, so it's a free platform that helps track your research data products, your software, and your data. It's maintained by a nonprofit. Um, it's domain independent. So in my view, I haven't seen great adoption within seismological community, but I think it has potential to be a useful platform for seismological researchers. So it's worth knowing about. And we've registered one of our data sets into OSF to see how kind of the benefits and the capabilities of that system. Next trend is science gateways. So I've mentioned these before. Quakeworx, we're going to be using that later this week, but it's a multi-domain activity, and growing collection of domains are developing science gateways to provide simpler access. And this is my simplified picture of a gateway works, um, browser-based interface to high-performance codes, and a list of potential benefits. Third trend here that I want to touch on is that the seismological community has started to use cloud-based data storage to manage very large data sets. So our experience working operating computers, if we're seismologists, um, it's not our specialty. We don't operate, we don't want to, many of us don't want to, we'd rather do seismology and not operate computers or storage. So the trend is to offload this into computer experts, cloud operators like AWS and Google and Azure. They will help us manage the data. In many cases, they'll store very large data sets for free, but the leverage or their commercial approach is now they expect the processing of the data to be done with their cloud computing resources. So examples of this: Google Earth Engine has a large data set. Open AWS has open data. The Sage seismic data is being moved into the cloud. There's ImageNet for AI training. These are all large data sets available from cloud resource providers. What this introduces is, it's in the future, computing is going to probably involve use of cloud computing services. And that introduces a collection of its own technology, kind of listed here: virtualization, containers, Kubernetes, cloud storage, structure as code, configuration management tools. All of these are kind of computing issues that are, are, are confronted with working with cloud computing. So although it's more to learn, it's likely you'll be faced with this in the future. The last comment here is talking about, is just kind of reflecting what are the disruptive or the transformative technologies. Several have emerged over the last, let's say, 50 years. Here's kind of a personal list I made: microprocessors, personal computers, GUI interfaces, networks, clusters, global internet, web browsers, search engines, cell phones. All of these had a kind of a major impact on how computing is done. In my view, machine learning methods and models appear to be the next disruptive technology. And as with these others, there will be advantages to being able to use this new machine learning and methods, these new disruptive technologies. So I like to make a distinction. There's a lot of discussion about machine learning methods in seismology. Me, I always try to establish early: are we talking about training a machine learning model, or are we talking about using a trained model? So if you look at, let's say, SRL, there's often articles about how they have trained their ML models, but it's less common where people are actually using their trained ML models. So for example, now it's fairly common to retrieve and use open source software, but it's much less common for someone to go and retrieve a trained ML model and use it for their purposes. But there will be advantages when we get to this. ML models have advantages. They can work better or run faster than current methods. So learning to use trained models is potentially a very valuable capability going forward. here's some places where you might go to find trained models. Okay, so sorry that went a little long, but that's kind of an overview and hope kind of a interesting introduction to some potential future trends.